This is AP Calculus BC, and in this video, I'm going to talk about section 5.5, which is all about the definite integral. And what we're going to discuss in this section, we're primarily going to talk about what an integral is, and we're also going to talk about integral properties and just the most basic way that we can calculate integrals, which is by using areas. So the first thing that I want to mention here is what we call a Riemann or a Riemann sum. There's multiple pronunciations for that. Some people prefer Riemann and some people prefer Riemann. I was always taught Riemann, so I usually say Riemann sums. But what this is just basically explaining what the notation of the integral is and what the overall meaning of an integral is. So when we talk about an integral, we've discussed this back in section 5.1 and a little bit when we were talking about rectangular approximation in the last section. The idea of calculating a definite integral is really the idea of finding the area between your function and the x-axis. And so you can see here with this summation that essentially what I'm doing is I'm adding up all of those rectangles. Each of the rectangles has a height of f of xi and a base of delta x. So that's the area of each rectangle, and then we're going to sum all of those up throughout our entire interval. Okay, so now where this goes from an approximation to actually being an integral where we're getting an exact value is when instead of using a finite number of rectangles, we then take the limit and say, okay, let's do this calculation as the number of rectangles approaches infinity, which means that the delta x or the width of each subinterval approaches 0. So you can see that's essentially what's going on here. In this summation, we're taking the limit as delta x approaches 0. So that's just making each one of those subintervals get infinitely small in width. And so essentially I've got an infinite number of rectangles. And what happens is the amount of error that I have with each one of those rectangles approximating the area on each subinterval, the amount of error then approaches 0, and I can get the exact value of the integral. So obviously we don't typically write an integral like this. We could, but that's not really the way we typically write it. So what we do is use a shorthand notation for integrals, which is what we have here. And in this notation, you can see that we've got that it sort of looks like an S. And if you remember, since we're talking about a summation, it makes sense that it would be essentially an S. But instead of writing all of that stuff with the limit as the length of the subinterval approaches 0, that's essentially what this is doing. So that's shorthand notation for that. And you can see a to b, that's indicating that I'm integrating this function on the interval from a to b. And then here's the same thing as what we had before, f of x dx. Well, f of x is still the function value on each of those subintervals. Dx is the width. And instead of having the delta x, we converted it to the dx. But again, it's just shorthand notation for that summation we were looking at just a second ago. Okay, so in terms of calculating these out, remember, like we've talked about, essentially what we're saying here is that if we can find the area between our function and the x-axis, that's going to be a representation of the integral value. And when our area is all above the x-axis, all we really have to do is calculate the area. So the problems you're going to see today are going to be a lot like this. We've got an integral from -2 to 2, and it's square root of 4 minus x squared dx. So one of the things I'm going to ask you to do today as you go through this assignment is I really want you to be sketching these things out so that you're getting a good representation in your mind of what's happening when we see one of these integrals. So I don't want you to think of this as a process. I want you to think of conceptually what's actually happening when I take an integral. What's actually happening here is if I look at the square root of 4 minus x squared, well, y is equal to square root of 4 minus x squared. If I want to think about what that graph would look like, square both sides of that, I'd have y squared is equal to 4 minus x squared. That's the same as x squared plus y squared is equal to 4. You should recognize that as a circle with a center at 0, 0 and a radius of 2. So the only difference is, had we solved for y from this final form, we would end up with y is equal to plus or minus the square root. Well, the negative square root would be the bottom half of the circle. The positive square root is the top half of the circle. So what we're looking at here is the top half of the circle. I'm going to say this is -2. This is about where 2 is, and then 2 out here as well. So I've got a semicircle that looks something like this, and the area that we're referring to is all of this area between that curve and the x-axis. So now, since we know this is a semicircle, this becomes a really, really simple exercise because we're just using basic geometry here. So I know it's 1/2 pi times radius squared. So my radius here is 2. And you can see that we have 4 pi divided by 2 is just going to give me 2 pi. Okay, so not really that difficult to do. That's what most of the problems are going to be like. But like I said before, I don't want you to think of this as some sort of magical process that's happening. I want you to think of this as, okay, this is the area between the function and the x-axis. Okay, so let's take a look at when we have area that's below the x-axis. So when we're calculating these things, essentially what we're doing when we integrate a function is we're thinking about the net change in the antiderivative function. So the amount that I change in the positive direction is above the x-axis. The amount that I change in the negative direction is below the x-axis. So an easy way to think about this is if you think of f of x in this case as like a velocity curve. Okay, so think about your velocity curve over on this graph. When I'm over here where the velocity is positive, obviously I'm moving in the positive direction. So the distance that I calculate on that first interval from A to that first 0, that's going to be how far I moved in the positive direction. Well, now on this second interval, I've got a negative velocity, right? And if I were to find the distance there, that would be the distance I moved in the negative direction. And then the last part of this, on the third interval from this second 0 to the right endpoint, you can see we're moving in the positive direction again. So in the end, that's essentially what we're doing is we're looking at the net change in the antiderivative function. Okay, so we always treat area above the x-axis as a positive. We treat area below the x-axis as a negative. And you can see this notation here. If the function is less than or equal to 0, then the amount of area we have is the negative of the integral on that interval that we're looking at. So if our function was negative, then we would essentially say, okay, knowing the function is negative, then the area is going to have to be positive. The area is the negative of the integral. In this case, with this graph that we have over here, we have both. We have area above and area below. So we would treat the two pieces that are above as positive and the piece below as a negative. Okay, so let's take a look at a couple of examples of this. So we have the integral from 0 to 2 of x minus 1 and the integral from 0 to 1 of x minus 1. So you can see the graph down below, so you don't have to sketch this one. Now, there are regions here, or a region where the area is below the x-axis, and we have a region where the area is above the x-axis. Now, if you think about this, you can find the area of each one of these regions because we know this is going out 1 unit. We know this would go up 1 unit. So if I found the area of that triangle, the area here is just going to be 1/2. This one's also going to be 1/2. So now in terms of the integral from 0 to 2, well, essentially what I'm going to do here is I'm going to take the area above the x-axis and I'm going to subtract the area below the x-axis. And in the end, I'm going to get 0. And again, think of that as a rate function, right? If x minus 1 was my rate function on the interval from 0 to 2, I went down by 1/2 unit and then I went up by 1/2 unit. So my net change is 0. That's essentially what that integral is representing. So if you can think of it in terms of a rate function, and I often refer to those motion problems because that's the most intuitive, simple application we can use. If you think of it as a rate function, it would make sense that essentially my displacement in that case is 0. Now, on the interval from 0 to 1, for this second integral, you can see we have area below the x-axis. So I know my integral value is going to be the negative of that area, and it's just negative 1/2. Okay, so not that difficult to do, and once you get your head wrapped around that part of it, this is actually pretty simple to deal with. Now, we do have some integral properties that we need to be aware of. A lot of these are going to be properties that are already intuitive because, again, an integral is a limit, like we've seen, and so the same properties that we've seen with limits and derivatives, we're going to have some of the same properties with integrals as well. But there are some special properties that only apply to integrals. And so one of them is this first property. And this first property, notice these limits of integration. The first one goes from B to A. The second one goes from A to B. So we're essentially changing the order of integration. Well, what that property allows us to do is it allows us to switch our limits of integration around. So there will be situations we'll see in another couple of classes here where we're going to need to switch the limits of integration to really make sense of the problem. And so if I come up with an integral, when I do my substitution into my problem, and I have an integral now of 2 to 0 of x dx, well, that's not as simple to reason through in your mind. So usually what we do is we rewrite this as the negative of the integral, and then we put our limits of integration in the correct numerical order. And now we can think of that area in the same way we always would. We can get the integral from 0 to 2 of x. We'd get an area above the x-axis, and then we know, okay, we need to treat that as the negative of that area because we switched the limits of integration. All right, the second property we have here is really basic, and this one's really obvious if you're thinking about what an integral represents. Notice the limits of integration here go from A to A. So if you're thinking graphically, if I were to graph this, what would it look like? Well, my interval doesn't have a width to it. So since my interval doesn't have a width to it, there's not going to be any area between my function and the axis. So regardless of what your function is, you can see over here we have a more complicated function, but as soon as you see limits of integration where the lower limit and the upper limit are the same, you always know that you're going to get a 0 for that. Okay, so the rest of these properties are, at least the next few properties are going to be properties very similar to ones that we've seen with derivatives and limits. The first one here, you can see we've got a constant multiplied to our function. We can factor the constant out of the integral. So that's pretty obvious and we've seen it, but this is going to be really important to us when we get into the idea of solving integrals by a method called substitution. So I can factor this -3 out of this integral and make it go from 0 to 2 still, and I would just have x dx. Okay, so fairly simple there. You can factor constants. You can move constants in and out of the integral, essentially. The next one here, I've got the sum of two functions, and it's really, we're kind of thinking about, okay, we've got multiple terms within our integral. Well, we can just break this into multiple integrals if we need to. And sometimes we would do that because we might have a situation where we need to use different integration techniques for the different terms within our expression. So, for example, on this next one, I have the integral of x plus 3 dx. I don't really need to separate this out, but I could separate it into the integral from 0 to 2 of x dx plus the integral from 0 to 2 of 3 times dx. Let's see, the next one I have here is just if I have limits of integration that are intersecting. So notice this first interval goes from A to B, and the second one goes from B to C. Also notice that the integrands are identical, f of x dx. So when you have a situation like that, you can actually combine that into a single integral. And so rather than having two separate integrals that I have to solve, I can say, okay, well, this is actually going to be one integral that goes from 0 to 2 of x dx in this case. We actually typically use that property in reverse, and you'll see it down the road when especially when we're dealing with something called improper integrals. Sometimes we're going to have limits of integration where we're going to want to actually break things apart into separate integrals, and you'll see why when we get there. But it allows us to work with functions that have sometimes weird things going on within the limits of integration. All right, property number 6 here. We're going to do an example on this one in a minute. This one, people tend to have a little bit of problems with this one at first, and it's actually really simple once you wrap your head around it. So what we're doing here is we're essentially looking at an integral that we're trying to solve, but let's say for some reason we can't solve that integral, but we have some basic information about this function. We know what the maximum value of the function is on that interval, and we know what the minimum value of the function is on that interval. So what that allows me to do is it allows me that even if I can't solve this integral, I can at least bound the value, meaning that I know the value has to be between two values. So it has to be above some number and it has to be below another number. And the way we do that is we say, okay, if we know what the maximum function value is, we know for sure the largest integral value we could possibly have would be treat the entire function as if it has that maximum value and then just multiply by the width. So the area of this rectangle here would represent the maximum that that integral could possibly be. And obviously, in most cases, I would know with my function, my integral is going to be less than that value, but I know for sure it can't be more than that value. That's really the point. And then the same thing with the minimum. We would say, okay, we know where the minimum is. Well, let's treat the minimum as the value of the function all the way through the interval. And if we did that, then the area of this smaller rectangle would be the smallest that integral could possibly be. So again, even though we can't solve the integral, we can at least say, okay, we know the value is, let's say, between 5 and 10. So now we've got at least an idea of what the end result is going to be, even when we can't solve it. All right, and then property number 7 here is really just talking about when we have functions where one function is greater than another. If we have a function that always has higher function values than a second function, then we know the integral of the larger function is always going to be the larger than the integral of the smaller function. And this is one of those things that's pretty intuitive, but where we use it a lot is when we have a function that's positive, we know the integral is going to turn out to be positive. All right, so let's take a look at a few examples where we're just going to practice with these properties, and then we're just going to do some practice just with integrals in general. Okay, so you'll see a few problems like this on your assignment in Wiley+, and they're fairly simple. So what we're given here are three definite integrals. We know that the integral from -1 to 1 of f of x is 5. We know the integral from 1 to 4 of f of x is -2. And we know the integral from -1 to 1 of h of x is 7. So what we're trying to do here is just make sure that you know the properties. Okay, so notice this first integral we're trying to solve has limits of integration that go from 4 to 1. So those are reverse of what we would like them to be because we know information about the integral from 1 to 4. But we also know if we switch the limits of integration, it's just going to switch the sign on that integral. Okay, so we have another one here. Limits of integration that go from -1 to 4. Notice these limits of integration, -1 to 1 and 1 to 4 intersect. So we could combine these two integrals into a single integral. So essentially 5 plus -2 is going to give me a value of 3. So knowing that I can combine those two things together. We also have one here that says the integral from 0 to 1 of f of x dx. Now, we don't know anything about the integral from 0 to 1, but we do know the integral from -1 to 1. So you might think, well, if I know that integral, maybe I could just break it in half and make it 2.5. The problem is we don't know what that function is doing on the interval from -1 to 1. All of this area that we have of 5 between -1 and 1, maybe that function has a value of 0 for most of the interval, and all of the area is between 1/2 and 1. All of the area between the x-axis and the function is between 1/2 and 1. So there's really no way for me to know. So in this case, you're going to get some questions like this, and it's because they're trying to make sure that you know which properties you can use and which ones you can't. So all you would write on a question like that is not enough information. And if you had this question on your homework in Wiley+, it's going to have that most likely as one of the choices on a multiple choice, and you would just choose that there's not enough information there. All right, and in a similar way, notice we have this integral from -2 to 2 now of h of x. Over here, we have information about -1 to 1. So again, first thought, you might think, well, I can just double it because the limits of integration, the width has doubled. Maybe it's just 14. And the reality is it could be 14, but we just don't know that because we don't know what this function is doing. So again, on this one, we would write not enough information. Okay, and then the last one, you can see that we've got the integral that goes from -1 to 1 of 2f of x plus 3h of x. So remember, we can think of this as two separate integrals, right? The 2 times f of x from -1 to 1. We can think of the 3 times h of x from -1 to 1. We can also factor the constants out. So essentially what I'm going to do is I'm going to multiply the f of x integral that I have from -1 to 1 by 2. That would give me 10. And then I'm going to multiply the h of x integral from -1 to 1 by 3, and that would give me 21. So in the end, I'm going to end up with 31. Okay, so those properties are pretty simple. Like I said, the main thing is you can only use the properties that are defined. You can't sort of create things based on what you think might be true. You can only use things if you're 100% certain that they are true. All right, and then the last one I want to go through is that property number 6 that we had over here. This property where we were talking about the minimum and the maximum. So that property can be used in a situation like this. We have the integral from 0 to 1 of square root of 1 plus cosine x dx. And we want to show that this integral is less than 3/2. So this is a good example of how we would use this property, because that's an integral that even when we talk about our more advanced integration techniques, we would have a very difficult time, if not maybe even an impossible time, trying to solve this thing out. So what we have to do is think about, okay, we can't necessarily solve this integral, but what can we do instead? Well, let's think about what function we're dealing with. We know our function is the square root of 1 plus cosine x. And we know we're dealing with that function on the interval 0 to 1. Okay, so that's the function that we're dealing with. Well, the maximum value that that function would have on 0 to 1 would be, we really have to think about when's cosine the biggest. Well, cosine's the biggest on that interval when x is equal to 0. So if x was 0, that would make cosine of 0 equal to 1. That means our maximum function value is square root of 2 on this interval. Okay, so that's just, we could figure that out if we wanted to, but really the main thing is we can just sort of look at it and know. So the maximum function value is square root of 2 on the interval from 0 to 1. So with that being the case, we can say, therefore, the integral from 0 to 1 of square root of 1 plus cosine x dx would have to be less than or equal to the square root of 2 times 1. Well, square root of 2 is what, around 1.4, so we know that's definitely less than 3 over 2. So all we did was apply that property using the whole idea of the maximum function value, and we know for sure that not only do we know it's less than 3/2, we know it's actually less than the square root of 2. Okay, so last part of this, you're going to have really the majority of your homework questions are going to be like this. It says use graphs to evaluate the following integrals. So right now, the types of integrals that we're going to look at are not going to involve antiderivatives when we're dealing with these definite integrals. So all we're going to have to do on this assignment is just think about simple geometry. So these are very, very easy questions to help you wrap your head around conceptually what's going on when we take a definite integral. So this first one, it says the integral from -1 to 1 of square root of 1 minus x squared dx. So again, I want you to sketch these at the beginning here so that you can get a feel for exactly what's going on. And if you have a problem like this, for example, on your quiz or on your test, I might have you actually show your work on a problem like this, and this is the work I would want you to show. So square root of 1 minus x squared. We saw one earlier, I think it was square root of 4 minus x squared. So we know this is a semicircle, and I'm just going to say 1's around here. So essentially what I'm looking at is this area in here, right? So that's my area. It's a semicircle. I know the value of this integral would be 1/2 pi times my radius squared. And in the end, I'm just going to get 1/2 pi or pi over 2. Okay, so pretty simple. Now, the next one, we've got the integral from 2 to 10 of pi times dx. So let's just think about this graphically. And this is actually a property that we can use here. If I have just pi as my value, this would be, let's say, y is equal to pi. Then regardless of what interval I choose, this is going to be the interval from 2 to 10, I'm always going to get a rectangular area. I know I didn't draw that the best, but you can get the idea that that would be a rectangle. So I've got a rectangle that goes from 2 to 10. So whatever the length of the interval is, which in this case would be 8, I know that it's just 8 times the height of 8 pi. Okay, so that would be really anytime you've got a constant value, you can just multiply that constant value times the length of the interval. Okay, now the next one, a lot of these problems are going to involve just really some of those prerequisite graphs that we talked about at the beginning of the year and using some basic transformation rules. So for this next one, we're looking at the absolute value of x minus 3. So absolute value of x minus 3, we should have an idea of what this is going to look like. We know this is absolute value of x translated 3 units to the right. So it's going to look something like this. And then I just need to think about, okay, what is this going to look like in terms of my integral? Well, in terms of an integral, here's what I'm finding here is I'm finding this triangle, and then I'd have another triangle over here. So those are the areas that I'm looking for. And if you think about that, that's 2 by 2, this first triangle. So this is going to give me an area of 2. The second triangle is going to have an area of 1/2, and that's just going to give me 5/2. Okay, and then we've got another one here, and then I'm going to have you try some of these as practice. So this time we have absolute value of x plus 1. Okay, same idea. I know this is the absolute value graph. I know it's shifted 1 unit to the left, and I know this is going to look something like this. And now I'm going from -2 to 3, and so that means I'm going to be out here in terms of area. And then 3 would be 1, 2, 3 out here. So this is going to be the area that I'm finding over there. And then just find the area of each one of those triangles. The one on the left is 1/2. The one on the right is essentially 4 by 4. So it's going to have an area of 8. And so in the end here, I'd get 17/2. Okay, so in terms of the geometry, what you're going to see are semicircles, triangles, rectangles. You might see some trapezoids. That's really it. Basic geometric formulas that you guys have known since middle school. So in terms of calculation, this is not difficult at all. So don't overthink this in terms of how am I going to solve this out. Keep in mind that these are intended to be very, very basic, because once we get into more complicated functions where we can't use these basic geometric shapes, we have to use other methods to solve the integrals out. Okay, so on this next page, there are a bunch of practice problems that I want you to try. So we've got, it looks like we've got 7 of them here. And when you get down here to the bottom, I want you to stop. And I want you to stop there because the last 3 are a little bit different, and I want to go through those with you. But I want you to try the next 7 questions and just see if you can solve them out. They're not difficult, but I want you to practice not just solving them, but also doing that quick sketch of the graph. So take a few minutes, just pause the video, take a few minutes, solve them out, and when you come back, I'll show you the solutions. Okay, so here's what you should have ended up with. And I didn't graph all of these just because I know you guys can sketch these things out. They're very simple. The first one, the way I did it was I used a trapezoid. Now, anytime that I say trapezoid, we can also break these into rectangles and triangles if you really want to do it that way, but I try to do it in the fewest steps possible. So I treated this as a trapezoid and got 18. The next one, I said, really, we've got symmetry here. So you can notice that I multiplied by 2 on that one. And the reason I multiplied by 2 is I said it's 2 trapezoids, and they are essentially reflections of each other over the y-axis. So I just found the one on the right, and then I multiplied by 2. And got a value of 12. Now, when you see things like the next one, you can always use the property that we talked about before, where we can think of an integral of multiple terms as the integral of each term separately. So you could think of this as the integral of square root of 144 minus x squared plus the integral of 1. And if you think about it that way, essentially what you have is a semicircle plus a rectangle. And if I do it that way, then the semicircle is got a radius of 12. I'm going to do half of that, and in terms of the area formula. And then I've got a rectangle that has a height of 1, a base of 24. Now, the other way to think about this is to say, okay, it's a semicircle, but now I've shifted it up 1 unit. So when I shift it up 1 unit, I'm creating that rectangle of area underneath the semicircle. So you can think about it either way geometrically. You're going to get the same thing. You can either break it into 2 integrals, or you can think about a semicircle shifted up 1 unit. Next one here, again, I did 2 trapezoids. So very, very simple. And this one's got symmetry again. You could also do a rectangle and a triangle. There's different ways to approach these a lot of times, but whatever makes the most sense to you. Here we've got a constant value of 75. So now we know that when it's constant, it's just the length of the interval times that constant value. In this case, we get 150. Here we've got a linear function. The only difference is that we've got an interval that goes from 0 to b. So I went ahead and graphed this one just to make it really clear. It doesn't change anything about how you evaluate. The only difference is now we've got sort of a general solution that regardless of what b is, we know how we're going to solve this thing out. And the last one that we have here, from a to 3a, or square root of 3a, same idea. So I know I'm going to go from a to a root 3, and I'm going to get a trapezoid, and it turns out the area of that is a squared. All right, so these ones at the bottom, I mentioned that these are just slightly different. And I want to go through one of them with you, and then I'll let you work through the other 2. So what we have here is the integral from -1 to 2 of absolute value of x over x. Now, we should know what this graph looks like at this point. We've seen this one a lot. And we did it with limits. We've seen it a little bit when we were talking about derivatives. So it's a really, really common function for us in this class. Now, remember, there's a jump discontinuity in this graph at 0, and the function is actually undefined at 0. So the graph looks like this. And remember, this is a value of 1, this is a value of -1, but it looks something like that. So if I go from 0 to 2, I know I'm going to have an area that goes here, and then out here is -1. I know I'm going to have an area that goes out here. Now, the thing that's weird about this is that we have this point at 0 that doesn't have a function value. But you have to think back to your definitions in geometry when you think about this. So in geometry, when we talked about the definition of a point, you have to think about, with a point, does a point have any dimensions? Okay, so remember, a point is just a location in space. It doesn't have a height, it doesn't have a width, there's no dimensions. So essentially what I can do here is I can eliminate that point at x is equal to 0. I can eliminate that from my calculation. I'm essentially going to ignore what's happening at x is equal to 0, because removing that point has no impact on the area of that rectangle. It has no impact on the area of that square. So that's really how we're going to deal with these when we have these point discontinuities. If we have a point discontinuity, then I can just take the 2 rectangles. The first one, it's really a square. It's below the x-axis, so it has an area of 1. We treat it as -1. The other one's above the x-axis, would be +2, and in the end, we get a value of 1. Okay, so again, anytime you have a point discontinuity like that, you can just ignore that point. Okay, so there's 2 more that are similar to this that I want you to try, just to make sure that you've got the understanding of this down. So pause the video, work through these last 2, and then I want to talk about those and just talk about how you need to be careful with this idea. Okay, and here are the last 2. Here's what you should have ended up with. You can see the next one's got a removable discontinuity at x is equal to 2. So again, no function value defined there. But I can remove that point, and I'm still going to get 21 over 2. The reality is I can have as many point discontinuities as I want within my interval. I could have 3 or 4 removable discontinuities. I could have 10. I could have 20. As long as we don't start connecting points together and creating an interval of discontinuity, I can take out point after point after point, and it's not going to have an impact on my overall area. Okay, then the last one here was the greatest integer function. So you can see we're going from 0 to 5. So I've got a lot of jump discontinuities here. I actually have function values defined at every point this time, but I have discontinuities in my graph. But I can still calculate the area underneath the curve for each one of those intervals. So you can see I drew in the rectangles. It didn't have any impact in terms of how we evaluate what that interval is going to be. Now, where you have to be careful, And you're not going to see this yet, but we are going to see this in the second semester. When you have an infinite discontinuity or a vertical asymptote within your limits of integration, we can't just ignore vertical asymptotes. We have to deal with those in a different way, and that's called an improper integral. So we'll deal with improper integrals at the start of the second semester. There's actually a method we have to use to solve those out. We've got to account for the behavior of the function around the vertical asymptote. So it's a little more complex. You shouldn't run into that now, but I just want to tell you that moving forward, don't just think that any discontinuity can be ignored. It's just that when we have these point discontinuities where I've got either a jump discontinuity, a removable discontinuity, those are situations where we can still evaluate the integral as if nothing special is happening at those points. Okay, so as far as your homework goes, you do have what's in Wiley Plus. I also attached this worksheet just for extra practice. You don't have to do this worksheet, but I wanted you to have it just for reference. What you can do with this is, use it as a supplement after you've done the assignment. I have the solutions for this posted on Schoology and also posted on the calendar in Schoology. So you can get to the solutions if you want to work through this. Like I said, it's totally optional. You might want to save this for right before the test. Use it as review material for this section.